Okay, so say we have two interreducible matrices A and B. Then we should convince ourselves that to go from A to B it'll take us some number of elementary row operations. So we're going to do induction on the number of operations it takes to go from A to B. So say that say that we need, and it doesn't really matter, n row operations to go from A to B. Okay, now we're going to do induction on the number of row operations. So the base case is that we don't need to do any of these. Say we can go from A to B in 0 row operations. Well, that means that A and B are equal as matrices. So A is equal to B. And then what that means is that we want to show that each row of A is a linear combination, or each row of B, I should say, is a linear combination of the rows of A, the first matrix. So that's easy because for any row in B, say row I in B, right, it's simply equal to what's a linear combination of the rows in A. If you take 0 of row 1, 0 of row 2, plus ... and then 1 of row I, right, and these are the rows in A, plus ... going down 0 of row whatever, however many rows, I don't know, n rows. And this is a linear combination of the rows of A making up any row in B. And that's the base case. Now, the inductive step is to say that we can go from A to B. We know that we can go from any matrix in k steps. And let's say we have a matrix that we need to go from A, or we can go from or if we have that we need, making a video. You want to be part of it? If we have that we need k plus 1 row operations to go from A to B, then there's some matrix right before we transform A into B, call it G, that we only needed k steps to get to, which means that every row, by the inductive hypothesis, every row of G is a linear combination of the rows of A. So then there exists G such that, G to be one operation, one row operation. And by inductive hypothesis, we know that the rows of G are linear combinations of the rows of A. So we're going to say rows of G are linear combinations of the rows from A. Now we need to prove that we can go from G to B, and if we have one row operation separating G and B, we just need to show that any row operation we do to G is still going to have it, that we can write every row of B as a linear combination of the rows of G, which would mean by our previous lemma that the rows of B are a linear combination of the rows of A, because a linear combination of linear combinations is a linear combination. That's what the lemma says. So we say that, let's go and get another page. Okay, so let's write our diagram. We can go K steps, let's say, for row operation to G, and then it's one step to B. So this is one step. Now, again, we know that the rows of G are a linear combination of the rows of A. Now, let's say that the row operation from G to B is a row swap. So the one step from G to B then obviously, the rows of G are linear combinations of the rows of A, and the rows of G with a row swap doesn't change anything. So the rows of B are linear combinations. The linear combinations of rows of A. And then now, what else could it be? It could be a rescaling, right? So now, if it's a rescaling, right? So let G be some row. Let G have row G, and then to go to B, Gi, right? Let's say we're changing row Gi in G by multiplying by some C, some scalar, right? And this is this is the row I in G, and then I do one operation, I rescale by some C, and then now this is the row I in B, right? This is beta I, and this is of course a linear combination of linear combinations. Gi is a linear combination of the rows in A, so clearly this ith row in B is also a linear combination of the rows in A, and we're done with this one as well. So we say rows of B are linear combinations of rows of A. And then the last one is the row combination. So you could again have some row I in G, and then what you're going to do is row I and row J, let's say. And we're going to change row J by a row combination. So I have these two rows inside of the matrix G. I'm going to take some C, multiply by Gi, and then add it to G row J. And we should see that this is also a linear combination of these two rows. So again, by the lemma, right, this is Gi is a linear combination of the rows of A, and G sub J is a linear combination of the rows of A. And then this is a linear combination of linear combinations, which is again a linear combination of the rows of rows in A. And now you're done because you did the base case and you did the inductive step. So we know that the rows of B are linear combinations of the rows from A. And we're done.